Hi guys, so Kenna here. Today we wanted to go ahead and talk about the role of water in life. Up to this point, we've been focusing on what are the characteristics of life, and one of the things that's come up a lot is that it's going to need or have water in it. So today, as we go ahead and start looking at water, here are our essential questions. Number one, in searching for life in the universe, why is it that we look for water? Try and figure out as we go ahead and start talking about all the things that water does for us, why, when we look to other planets, other moons, is it that we are seeking water to really kind of give us evidence that life could exist there? Central question number two: what are solutions, solvents, and solutes, and how are they related? Now, I realize that some of you may have gone over this in physical science last year, but it's always good to review key vocabulary and helping us understand how these things behave. And number three, what does it mean to be polar? This is going to be a very important term for us, not just in these set of notes, but as we go ahead and move throughout this entire semester, and even when we go ahead and get a little bit into next semester as well. And when we look at that term polar, what properties does that give to water? Now, human ideas on what exactly constitutes a living organism are very reliant on the study of life here on Earth. We don't have any experience with life beyond Earth. We've actually not found any to date. We do have to think about life as we know life here on our planet, and that largely evolved and exists because of water. We have discussed the difficulty of creating a universally agreed upon definition for life and have instead focused on various characteristics of life. These are the common list of characteristics of life that you typically will see. Number one, you guys mostly came up with this. Most life as we know it is made up of cells, and this is going to be what we call cell theory. We'll talk a little bit more about this later on as we start talking more and more about cells. Those cells have to be able to go ahead and make new cells. That happens either through sexual or asexual reproduction, but you have to be able to reproduce to make new versions of that cell. The instructions for that comes in the form of some genetic code, universal genetic code. On Earth, we really focus on DNA. We'll talk a little bit about RNA because there are some examples of that as well, and what that might look like if we were to go to another planet. You guys almost universally got this one, growth and development. In order to be alive, something needs to be able to grow and develop over time. But we talked about the limitations of this particular characteristic when we started looking at an analysis with fire. Also, many of you came up with the topic we need for materials and energy. This is what we call metabolism. You may have heard one of your friends or family members talk about, oh, I have a fast or a slow metabolism. Uh, that seeming to justify why they had a lot of extra or a lot less weight than maybe somebody else does. One of the key ones that I think our discussions brought up was that things that are living need to be able to respond to their environment. They respond to a stimulus. These are any event or occurrence or changes in the environment around them that causes the organism to have some sort of change. We also had a few of you go ahead and talk about this idea of maintaining an internal balance, this process we know as homeostasis. And then a few groups also came up with this idea of evolution. So you might pause the video here. This would be a great list of characteristics of life for you to go ahead and refer back to as we go ahead and move on throughout this course. Now, some of these we will talk about in the first 6 weeks, and some of them we'll go ahead and talk about later on in the course. All right. There are two central features, however, of our current search for extraterrestrial life. These focus on carbon chemistry, which we will start going over next unit. Well, start going over next class. And then the use of liquid water. So before we go into getting deeper in macromolecules and those important biological molecules of carbohydrates, lipids, nucleic acids, and proteins, The other big factor is the look for water. And so that's what we're going to focus on here today. Now, I want to go ahead and start with a video, and then we'll go ahead and discuss a little more all the things that water does. All right. So here we'll watch this video, and then we'll go ahead and talk about the characteristics of water.
Water, an essential element to life. It touches every aspect of our lives, from public health to safety to the foundation of our economy. We put water to work in a million different ways, but do we even know its true value? We are so used to turning on the faucet and having access to safe water 24 hours a day, 7 days a week, that rarely do we stop and think about the complex systems and technologies needed to treat and deliver this vital resource. Throughout history, people have always relied on water for survival. It dictated where they lived, where they traveled, and whether or not they survived. Today, we can see remnants of ancient water networks, such as the Roman aqueducts. Huge structures were formed to channel water throughout an empire. Fast forward to the year 1652, and America built its first distribution system. Farmers with wells started selling water to others, and Boston residents were the first to enjoy a centralized water system, something critical to protecting communities from the ever-present threat of fire. But real progress came just before the Civil War, when iron pipes replaced wooden ones. Until the early 1800s, the use of wooden pipes made from bored-out logs was common practice, and some are still in place today. By 1890, there were more than 600 water suppliers in the U.S., but public health problems such as cholera, smallpox, and typhoid plagued cities. In 1908, a major breakthrough occurred in Jersey City, New Jersey, when a disinfectant in the form of chlorine was added to the water. Within a few years, chlorine was being used nationwide and virtually eliminated the spread of waterborne diseases, making it the single most significant public health development of the 20th century. Today, water suppliers use a variety of treatment processes to remove contaminants. Raw water travels from its source to the treatment plant and later into hundreds, even thousands of miles of water pipes before reaching your home or business. In fact, the U.S. water infrastructure is so large that it spans 30 times the size of our interstate highway system. But with that comes a unique set of challenges. Water is not easily transported. It is heavy and cannot be compressed. 1 gallon alone weighs more than 8 pounds, and an enormous amount of electricity is required to help it move within the distribution system, making its transportation costly. Laws such as the Clean Water Act and Safe Drinking Water Act, set forth by the United States Environmental Protection Agency, establish quality standards to help protect public health, safety, and the environment. These quality standards are among the toughest in the world and continue to evolve. So water utility companies are regularly investing in sophisticated and expensive treatment technologies such as UV, membrane, and reverse osmosis to keep us safe and ensure an adequate supply of drinking water. As a result, today our drinking water is safer than it was 20 years ago. Another challenge is that the systems and networks used to bring water to us do not last forever. All infrastructure ages, and the same is true of water's unseen pipes and transport systems. Most of our water infrastructure is from the first half of the 20th century, and it is estimated that within the next 30 years, it will reach the end of its useful lifespan. In order to protect quality, public health, and the reliability of our water services, these aging and failing pipes will need to be replaced. Current estimates indicate that will cost at least $1 trillion over the next 25 years. Water is the only utility that is ingested, and the cleaning and delivery of water is 3 times more capital intensive to provide than any other utility. Yet historically, most consumers pay less for it than gas or electric. A typical American household uses 260 gallons of water every day, making our nation's water footprint among the largest of any country. Currently, most Americans pay less than $3.75 for every 1,000 gallons of safe water delivered, a relative bargain compared to the rest of the world. Because the cost of installing and maintaining water infrastructure is so high, it usually discourages companies from creating duplicate systems and competing. This means in most areas, water service utilities operate as a monopoly. For over 200 years, privately owned and operated water utilities have been providing services to American communities. In fact, 73 million Americans currently receive their water from a private water company. Water systems owned and operated by private water companies deliver 4.6 billion gallons of water to their customers every day. And while it might be easy to think they're simply selling a commodity, the truth is they are providing important services and the infrastructure required for the treatment and delivery of safe and affordable water. Private water utilities are regulated at the state level by Public Utility Commissions, or PUCs, who work with private water utilities to determine rates. In this process, PUCs look at how much is being spent to create, maintain, and operate water systems, as well as the quality and reliability of service. They then establish rates with input from the public, balancing both the interests of the water customers and the private water utilities. This transparency ensures that both the consumers' and utilities' needs are being met. Safe and reliable water service is the lifeblood of our nation, essential to the survival of every individual, family, and business. With millions of miles of pipe, thousands of water treatment plants, and distribution systems that stretch to every corner of our nation, the job of safeguarding water is one that we all must share. As our nation's population continues to grow and increasing pressure is placed on our resources, communities will need the experience of the private water industry more than ever to protect public health, promote environmental stewardship, and deliver sustainable solutions. Their expertise in the development and implementation of technology, alongside the replacement of aging infrastructure, will have a profound impact on people, businesses, and the environment, because wherever there is water, there is a well of opportunity.
Okay, so water is a pretty important thing for us, and we are pretty fortunate to live in a country that has so much available water for us to use. That may not always be the case. Water is fairly common in the universe. It's found everywhere from interstellar dust clouds to the orange-red fields of Mars, but most of the water that we see in the universe is in the form of ice. Solid water can't act as a lubricant for the molecular processes of life, so the search is for liquid water, a commodity that is far more rare in the universe. If we accept that any form of life will require a comparable degree of chemical sophistication, it is hard to see what other solvent might allow this to happen. Life most probably needs some sort of solvent for chemical reactions to take place in. That solvent will need to perform an active, diverse, and flexible role. It can be a reactant, it can be a product, it produces a whole bunch of different features for chemical reactions. Water is so far the only common liquid that we know that is capable of these particular roles. So either directly or indirectly, water affects all facets of your life. Without it, there would be no vegetation on land, no oxygen for animals to breathe, and the planet would look completely different than it does today. Water is necessary to keep people's bodies and the environment healthy and should be valued and protected as the precious resource it is. Now, before we move on, do any of you know how much of your body is made up of water? You probably said something in the order of 70%, and then you would be right. That's a lot. That's 70% of your body by weight is made up of water. So if somebody weighs 100 pounds, 70 pounds of that is water weight. Okay, the other 30 pounds is all the other stuff that makes you up. This is not abnormal though, as most known living organisms are between 50 and 90% water. Your body can lose nearly all of its fat and over half of its proteins and still be alive. But if you lose 10 to 15% of your body's water, you're dead. Okay, so just what does water do inside our bodies? Water is a very simple molecule. It's formed with what we call a polar covalent bond. Polar simply means that we unequally share the electrons that are in those outer valence shells. Okay. So water is a polar molecule, and you'll notice here as we go ahead and start looking at the water molecules that the positive charge is up here at the top by the oxygen. The electrons spend more time around the oxygen, and its positive is down here by the hydrogens. So the electron, which is negative, spends less time around the hydrogens. This structure of negative on one side and positive on the other is what makes it polar. But this also means that water molecules are attracted to each other. Okay? Now, being attracted to each other like this uh, causes water to create what is known as a hydrogen bond. Okay? So the attraction between those partial charges on the hydrogen end and the oxygen end is what we call a hydrogen bond. This ability to create these hydrogen bonds and to be this type of polar molecule makes water excellent solvent. It's really good at dissolving a whole bunch of different substances. It's ideal for dispersing organic and inorganic molecules, as well as facilitating a whole bunch of cellular level chemical reactions. Good example of this would be its role in our kidney. Our own kidneys and water's solvent properties make a great pair. This is what really keeps us alive and healthy. Your kidneys are responsible for filtering out substances that enter your body from the foods and drinks that we consume. But the kidneys have to get rid of the substances after they accumulate too much. That is where the water helps out. Being such a great solvent, water washes through the kidneys and dissolves these substances that start to accumulate there and sends them on their way out of our bodies. Okay? If you've ever gone ahead and taken salt or sugar and tried to dissolve it into water, you're looking at the solvent properties of water. Here's an example with sodium chloride or table salt. We put the table salt into the water, you begin to stir it up, and the sodium and chlorine begin to disassociate and dissolve into the water, but they're separating because of the polar nature of those molecules. If you were to zoom in, you would see something like this. You start seeing that some of the chlorines get separated from the sodium ions, and because of that, those partial positives are around the negative chloride ion, and some of those negative oxygens are around the positive sodium ion. Okay, so the ability of a substance to dissolve is called its solubility. Now, this is where it's important to remember from your physical science classes these three terms: solute, solvent, and solution. The solute is the substance that dissolves to form a solution. The solvent is the substance in which the solute dissolves. And the solution is what is produced when a solvent dissolves the solute. So the mixture of the two of them together. So the following rules can be used to decide whether something is a solvent or solute in a solution. There are three states of matter: solids, liquids, and gases. Any reagent that undergoes a change in state, going from a solid to a liquid, liquid to a gas, this type of thing, is typically known as the solute. If neither reagent changes shape, changes state, the reagent present is the one in the smallest amount is the solute. Okay, so the solute is what you have less of, and the solvent is the one you have more of. Water, because of its polar structure, also it produces two traits, what we know as cohesion and adhesion. So cohesion is the ability of materials like water, it doesn't have to be just water, but it's the ability of things like water to be attracted to other molecules of the same thing. Water has a very stable temperature. This is why the oceans don't evaporate super easily. This is why they don't freeze super easily. But inside our bodies, this is why we don't have huge fluctuations in temperature. Okay, you don't see your body get super hot or your body gets super cold. So this keeps us at a pretty stable internal body temperature. Water also exhibits, because of cohesion, surface tension. On the top of water, there's almost like a little film. This film is what allows things like water striders to go ahead and quote unquote walk on the water. Okay. In the lab that you'll go ahead and see demonstrated for you today, or you can try this at home on your own, you're going to get a chance to, what most people would say is float a paperclip on top of water. Now, the paperclip's not actually floating because it's more dense, and if you were to put it straight down, it's going to sink. But if you gently put it onto the surface, it's not going to break the surface tension. The cohesion of the water molecules is stronger than the mass of the paperclip to break through because it's more dense. Okay. So these are the water striders I'm talking about. Now, if you look at this picture, I always like this picture because this gives you a good demonstration of what we're talking about in terms of walking on the water. If you take a look right here, okay, you can do this for any of the legs. You'll notice that the leg here is actually sitting on top of the water. It's not actually in the water. So when the water strider is finished going across the surface of the water, it comes out completely dry because it was never actually wet. It was never actually in the water. Okay, now is there anything that does this that's a much larger organism? The answer is not much bigger can go ahead and do this. One of the largest things we know about that can do this is what's known as a basilisk or Jesus Christ lizard. And so it's able to distribute its weight enough that it can, for short distances, run across the surface of the water. Next time you're at a pool or at the river, I encourage you to give this a try. It's a much more difficult task than you can possibly imagine. Notice the positioning of the legs, of the tail, that allow it to go ahead and spread its body weight over a huge amount of space. Okay. When you look at this basilisk lizard behind, it's got very long, thin toes and a long body that allows it to spread that body weight out. What else does surface tension do? Well, surface tension also makes water stick together. Well, I used to teach astronomy for many years, and one of the things that kids would always ask is, can you cry in space? There's a beautiful scene in Gravity where Sandra Bullock's character cries in space. But in reality, it doesn't work the way that it does in the movie. Water molecules are going to stick together, especially if there's not gravity to pull them down. This is important because it allows you to keep your pulmonary function, your lungs functioning better. But when you go ahead and start looking at how this works, it doesn't really allow you to cry in space.
So here's a common question. Can you cry in space? Do tears work? Well, let's try it out. I can't cry on command, but I'm going to take some water, drinking water, put it in my eye just as if I was crying, and let's see what happens. Get myself nice and stable for you here. Here we go. So, just as if I started crying, my eye is full of tears. But you can see it just forms a ball on my eye. In fact, I can put more water in. And so if you keep crying, you just ended up with a bigger and bigger ball of water in your eye. Until eventually it crosses across your nose and gets into your other eye, or evaporates, or maybe spreads over your cheek, or you grab a towel and dry it up. So yes, I've gotten things in my eye. Your eyes will definitely cry in space, but the big difference is tears don't fall. So grab.
Okay, so when we start looking at this is kind of cool. The next property we want to talk about is adhesion. So while cohesion is a molecule sticking to a like molecule, water or something like that, adhesion is where that molecule sticks to something other than itself. Now, in your physical science class, you may have done readings through a graduated cylinder. And if you go ahead and take a look at a graduated cylinder, okay, one of the things when you're measuring it that you have to go ahead and look for is that there's this little bow, okay? Does anybody remember what that little bow is that you have to read from the bottom of? Yeah, this is what's known as the meniscus. And so we always read from the bottom because on the sides here and here, the liquid is climbing the side walls of the graduated cylinder. Okay, this is because of adhesion. Now, we can actually see this in anything from a straw, but what we would typically do in a lab is use what's called a capillary tube. Okay, so surface tension is related to cohesive properties, but capillary action is related to both adhesive and cohesive properties together. So if you put a straw in a cup and next time you get coffee or something like that, you can go ahead and give this a try, you'll see that the liquid climbs a little bit up the straw, and the narrower the straw, okay, the farther the liquid's going to go up because it has to fight that strength of gravity. Okay, so capillary action is limited by gravity and the size of the straw. The thinner the straw or tube, the higher up the capillary action is able to pull it. And in fact, plants take advantage of capillary action to pull water from the ground all the way up to the top of their very tip top canopy. So think about like a coastal redwood. They're going to go ahead and use these tiny cells known as tracheids, which are part of the xylem, to pull water from the ground and the bottom of the roots to the very top of these ginormous trees. They get a little bit of assist from something known as transpiration, but a lot of this is through capillary action. What else? So water acts like a buffer because we can go ahead and break it apart to produce hydrogen ions and hydroxide ions. We can use it in acid-base chemistry. So I don't know if you're familiar with acids and bases from physical science last year, so let's talk briefly about it. Acids and bases are common solutions that exist all over the place. Most of the liquids that you'll encounter in your daily lives are somewhat acidic or somewhat basic. Very few are actually neutral in the middle. Their only exception to this is pure water. Okay, they have completely different properties and are unable to neutralize to form water. So some good examples of these things: acids include lemons, oranges, citric acid, right? Vinegar, urine, sulfuric acid, hydrochloric acid. Okay, acids, if you're identifying them chemically, will typically have the little hydrogen by itself. So if we take a look here, HCl, Cl is chlorine, H is hydrogen. This isolated hydrogen ion right here is what makes this an acid. Okay. Similarly, when we go ahead and start looking at bases, things like soap, most of your cleaning agents, if you ever do oven cleaner, that's a really strong base. And a lot of people think about bases as being less dangerous. They're not. A really powerful base is just as dangerous as a really powerful acid. If you're trying to identify bases chemically, you have a chemical formula like this. This is sodium hydroxide. Okay, you've got your Na over here, sodium, but there's your OH, your hydroxide. This is what makes it a base. So up here, the hydrogen by itself makes it an acid. The hydroxide down here makes it a base. Okay, all right. So those are good examples of acids and bases, and we look at them on what we call a pH scale. Acids are those that have more hydrogen ions than they do hydroxide ions, and they have lower numbers on the pH scale. So your strongest acids are going to have a pH really close to 0. Okay? Bases, on the other hand, have more hydroxide ions than they do hydrogen ions. And so they're going to have much higher numbers on the pH scale. Things like oven cleaner are going to be about 13.5, getting closer and closer to that high 14 on the pH scale. Okay, so you can see here as you go above 7, you're increasingly basic. As you go below 7, you're becoming increasingly acidic. And because of all these properties we've talked about, you get to use water as this amazing chemical that's involved in so many chemical reactions. It facilitates digestion. Okay, can you imagine trying to eat food without liquids inside your body? Just slide it down dry. That sounds horrible. It helps you to transport materials throughout your body. And excretion, you guys know what excretion is? So this is the elimination of your waste products. Imagine trying to go ahead and eliminate waste. Try peeing without water, okay? That would be horrible. It's more like urea that you see when birds poop. Okay, when birds poop, that little white part is the urea. That's the bird urine. Okay, they don't use liquids for it. You may have heard the old saying to a brick, well, you literally would if you didn't have water. Okay, so water is everywhere. It's in almost every chemical reaction that takes place in your body. It's a reactant, it's a product, it's used all over the place. And it's a good thing that we have so much water in us. Remember that we are about 70 to 75% water by weight. Okay, and you can only lose about 10 to 15% of that before it actually can kill you. Now, 30 to 40% of that is found outside in your fluids. 60 to 70% is actually found inside the cell as part of what we'll talk about later as the cytoplasm. Okay, so when searching for extraterrestrial life or just valuing the life we have here on our planet, water is incredibly crucial to the life processes because it is a polar molecule that is able to catalyze tons of reactions, and it has those properties of cohesion and adhesion, which allow for surface tension and capillary action. All right, I hope you guys enjoyed the presentation. Have a great rest of your day, and I'll talk to you soon. Take care of yourselves. Bye-bye.